All right, in this video, we're going to go over some of the concepts and definitions to probability. So think of this as an intro to probability. All right, so let's start off with some definitions here. So a probability experiment. So what's a probability experiment? It's an action through which results are obtained. So think of an experiment as doing something, right? So common probability experiments involve, flipping a coin, or rolling a six-sided die, or selecting a card out of a deck of cards, or selecting a person out of a crowd of people. All of those are probability experiments. Okay. So what's an outcome? An outcome is the result of that experiment. When I flip a coin, when I flip a quarter, right, my outcome will either be heads or tails. When I roll a six-sided die, I'm going to land on either 1, 2, 3, or 4, or 5, or 6. I'm going to land on one of those numbers. Okay? A trial. A trial is each time you do your experiment. So if my experiment is flipping a coin, each time I flip a coin, that's a different trial. Every time I roll that single die, so die is singular form of dice. When I roll that singular die, that's a trial each time I do it. So what's a sample space? A sample space is a collection of all your possible outcomes. And we're going to see these in examples in just a second. But a sample space is just a listing of what are all the possible ways or outcomes I can get from my experiment. And lastly, an event is a subset of your sample space. It's like you're saying, I only want certain things to happen in my sample space. So let's go through some examples here, and hopefully it'll clear up the definition of these probability terms. So for example, let's make this a little bigger. Suppose our example involves flipping a coin 3 times. What is the sample space? And what are the outcomes in the event that we get a single head? All right, so let's take this one kind of part at a time. So we're flipping a coin 3 times. And so that is our experiment. So one trial will involve 3 things happening, all right? It's going to be the result of each time that we flip that coin. So I'm going to let S, okay, represent our sample space. Okay, so S represents sample space. All right. So what are the things that are included in our sample space? Well, let's see here. I'm going to use, we call it a curly bracket to denote a set, right? So a sample space is a set of things. So let's say we're flipping this coin 3 times. Let's say we flip it one time, we get a heads. We flip it another time, we get a heads. And then we flip it a third time, we still get heads. So what we have here is the case where we ended up with 3 heads. All right, so I want this to be clear. This is one outcome because we flipped that coin 3 times. Because our experiment is flipping a coin 3 times, that is one particular outcome. Well, what else could happen? Let's see, I could flip that coin one time, get a heads. A second time, I could also get a heads, but this third time, I could get a tails. That is another outcome. Okay? In fact, we're going to have, for this particular experiment, we're going to have 8 different possible outcomes. So I'm just going to write them out to save a little time here. Heads, tails, heads. We can have tails with 2 heads. We could have TTH. What else? A THT. And we could have a HTT. And then we could have all tails. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So those are all the possible outcomes for our experiment of flipping a coin 3 times. A good practice, if you want to, I want you guys to practice this at home. Practice what's the sample space if I ever learn how to write. I want you guys to practice, what's the sample space whenever we toss the coin, for tossing a coin 2 times? A coin twice. Okay, so see if you can come up with the sample space for that. And I'll let you know for that one, there's going to be 4 outcomes in that experiment. So that'll be good little practice for you guys to go through. Anyways, that is our sample space whenever we flip a coin 3 times. Now the next part of this question says, hey, what are the outcomes in the event where you get a single head out of those 3 tosses? Okay? And I'm going to use the letter E. We can use whatever letter that you want, okay? So don't get caught up with the letters that we're using here. But we're going to let E represent event. And I want us to go over what are the outcomes that will go in E. So we need to get a single head, all right? So I'm going to go back up to my sample space, and I'm going to highlight those entries, okay? Well, the places where we get a single head involve, let's see, THT has just 1 head. HTT has just 1 head. And TTH, I forgot about that one. So let's see, I don't see any other outcomes that have exactly 1 head. So therefore, the outcomes in our event, E, will be exactly those. TTH, THT, and HTT. Okay? So that's exactly what an event is. It's just a subset or some of the outcomes from your sample space. All right, moving along here. The next concept we're going to cover, and the namesake for this chapter here, is how do we find the probability of an event. All right, so the probability is the likelihood that something happens, right? Well, to find the probability of event E happening, let's say we have an event and we call it E. The probability of event E is that we take the number of outcomes in E and we divide it by the number of outcomes that are in the sample space. Basically, it's the number of ways I can win a game divided by the total number of ways I can play the game. Okay, hopefully that's not a foreign concept. So for example, using the previous example of tossing a coin 3 times, what's the probability that we get 1 head? Okay. Well, if we go back here, remember that our sample space contained 8 different outcomes, right? Our sample space had 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. Okay, so the sample space had 8 outcomes. And our event, right? Our event had 3 outcomes. So our event had 3 outcomes. So the probability that we do something in E, in event E, for our particular example, so the probability of event E, that is going to equal the 3 outcomes that were in event E divided by the 8 total outcomes in the sample space. So there's a 3 out of 8 chance that we do something in event E. All right, moving along here. A few more concepts. So far, the examples that we have come across involve what's called a theoretical probability. And so a theoretical probability are probabilities that arise when there's an equal chance for each outcome occurring, right? In this case, we're talking about whenever we flip a coin, right? There's an equal chance that we get either heads or tails. There's a 50-50 chance if we use a fair coin. Whenever we roll a single die, right? A fair die, there's an equal chance that we land on 1, 2, 3, 4, 5, or 6. Those are theoretical probabilities. So what are some examples of probabilities that are not theoretical? Let's say we wanted to randomly select a person that is a Democrat, for instance. There's not an equal chance that everyone identifies as being a Democrat, right? So in that case, we would use something called a subjective or an empirical probability. Maybe we'll get into that later. But theoretical probabilities have a relationship to this thing called the law of large numbers. It's a very important concept, especially if you like to play in the casinos. The law of large numbers states that as we perform a large, and I'm talking about a extremely large amount of trials, the probability of an event occurring will approach its expected probability, its expected value, right? But here's the most important part. Note that the law of large numbers says nothing about what happens in the short run of these trials that you're doing. Okay? So what this means is that if we were to look at an extremely large amount of trials of, let's say, flipping a coin, right? We're looking at millions and millions of trials of flipping a coin. Well, yes, we expect roughly 50% of those outcomes to be heads and 50% of those outcomes to be tails, right? However, in the short run, there's no rule that says we expect 50% heads and 50% tails. And I think this next example illustrates that. So for example, let's say we are tossing a coin. We've tossed 10 straight heads, okay? What's the probability that your next toss will be heads? And also, should you expect the tails on your next toss? Well, because, once again, we're dealing with a theoretical probability situation, every single toss is what we call independent, and we'll touch on that concept in just a second. But what's the probability of my next toss? Even though I've got 10 straight heads, the probability of my next toss will be heads is still 50%. Okay? Probably the next toss is 50% because, right, there's a 50% chance you get heads or tails. Basically, whenever you're tossing a coin, it has a memoryless property. It doesn't remember what you did before. Okay, should you expect a tails on the next toss? We've tossed 10 straight heads, right? That does seem a little weird, but should we expect a tails on the next toss? We should not. Okay, very important. We should not expect a tails on the next toss. Okay, and why is that? I'm saying that there's this kind of concept of the law of averages, right? Like I'm due for a heads, right? Or I'm due for a tails. No, in the short term, there's no guarantee that you're due for anything, right? All we can say is that in the very, very long term, then yes, things will begin to even out. But in the short term, we have no idea what's going to happen. So if you ever go to the casinos and you win a good amount of money in the short run, but you have some idea of like what's the average amount of people, money that people leave that casino with, and it's a lot lower than what you're winning, know that if you stay in that casino long enough, you will start to see your money go down. You'll start to lose money and approach that average, okay? So that's where this law of large numbers is very helpful when you're playing in the casinos. All right, the last two concepts are often confused with each other, so hopefully this will clear it up. Let's talk about disjoint events, or sometimes called mutually exclusive events. Two events that cannot occur at the same time are called disjoint, or sometimes mutually exclusive. So two events that cannot occur within the same instance are disjoint. So a couple examples here. Suppose our experiment involves randomly selecting a single person. We're selecting one person. Let's let M be the event that the person is male. And let's let P represent the event that the person is a professor. Okay? Are these two events disjoint? Okay? Once again, disjoint means in a single instance, can both of those attributes occur at the same time? Well, can we select a single person that is both male and a professor? Well, I certainly hope so, right? Because I like to think I fit in that category. So because male and professor can occur at the same time, we say these events are not disjoint. Okay? Not at the same time, excuse me. These events are not disjoint. All right. So if they can occur at the same time, they are not disjoint. If they cannot occur at the same time, they are disjoint. I know it's a little confusing, but hopefully that clears it up. Let's do another example. Suppose our experiment involves randomly selecting a single person again. Let's let J represent that the person has a birthday in June, and S represents the event that the person has a birthday in September. Okay? Are these two events disjoint? Once again, when we talk about disjoint events, we're talking about in a single instance. We're selecting a single person. Can a person, one person, a single person, have a birthday in both June and September? Is that possible? That is not possible. Therefore, these events are disjoint. All right? We cannot have a birthday. A single person can't have a birthday in both of those months. All right, a concept that's often confused with disjoint is the notion of independence. And I'll make a disclaimer now. We're going to go more into the mathematical sides of independence in the next video. But right now, I just want to go over the concept. Two events are said to be independent if the occurrence of one event does not affect the probability of the other event occurring. So if one event happening has nothing to do, no effect on the other event occurring, we say the two events are independent. If the occurrence of one event affects the likelihood of the other event occurring, then we say the two events are not independent, aka they are dependent events. So let's see here. For example, consider the following two events. Let event A represent the scenario when a woman has what's known as the BRCA gene. So this is called the breast cancer gene. So A is when a woman has the BRCA gene. Okay, it's just a mutation of the gene. Let event B represent the case where a woman develops breast cancer. Okay. Well, our question is, are these events independent? Well, research has shown that a woman that has this BRCA gene has a higher likelihood of later developing breast cancer. So because that is affecting those two events, right? Because if I have A, then I have a higher probability of developing B, breast cancer, we say that these two events are not independent. These events are dependent. Right? And it's kind of in the name, right? Because the likelihood that I get breast cancer, it depends on, do I have this BRCA gene or not? All right, let's look at this example. Consider the following two events. Let's let A represent the scenario where a person has type A blood. And we're going to let event B represent the scenario where a person has type B blood. Okay? Question is, are these two events independent? Well, if I have type A blood, how does that affect your likelihood of having type B blood? It doesn't, right? And I'm sorry here, I've probably left out something that we should know, but we're assuming that, these people are not related or anything. Yeah, because I have type A blood, that has no effect, no impact on you having type B blood. Because of that, we say that these events are independent. All right, lastly, a quick little blurb. So as I said, disjoint and independent events sometimes are confused, but just know this. We note that disjoint events cannot be independent. It just can't happen, right? Because when we have disjoint events, that means that the occurrence of one event, it certainly affects the outcome of the other event occurring. So disjoint events will lead to a set of dependent events. Anyways, as I said, in a future video, we'll touch more on how do we mathematically verify that we have an independent set of events. Anyways, I hope this video helps you out, and I'll see you guys in the next one.